Hello, everyone. In this video, we are going to look at problem 2 from our section 3.5 on related rates. So for this problem, before we get started, you might want to take a brief look at the recommended steps in a related rates problems, just to refresh yourself on how we go about solving these types of problems. All right, so let's launch in together. So we have a ladder that's 10 feet tall, leans against a vertical wall, and the bottom of the ladder slides away from the wall at a speed of 2 feet per second. When the bottom of the ladder is 4 feet from the wall, find the rate at which the top of the ladder is sliding down the wall and the rate at which the angle between the top of the ladder and the wall is changing. So step 1, what is it? Draw a picture. So I'm going to draw a picture of my ladder here. So here's my ladder. Because we don't even really know what shape, geometry, function we have to use yet before drawing our picture. So here's our ladder. It's a wobbly one. Okay, cool. So now this ladder is against a wall. Here's our wall and the ground. So now we can start to see some geometry that we'd want to use. So let's call Y then the height from the top of the ladder to the ground. And let's call X the length from the bottom of the ladder to the wall. And we see that we need to know these quantities. Oh, and 10 is the length of our ladder. So our ladder is 10 feet long. The bottom of the ladder slides away from the wall. So we need to, that's our X. When the bottom of the ladder is 4 feet from the wall, we need to find the top of the ladder, which is Y. And then the angle between the top of the ladder and the wall. So here's the top of the ladder, here's the wall. So we're going to call that angle, let's just call it theta. So now we've done step 1. We've identified the diagram and the variables that are changing the diagram that we want to find some info about. So now what else? Well, we are given some information. We are given that the change of X with respect to time, that's the rate at which the ladder slides away from the wall, is equal to 2 feet per second. And what we're told to find in part A and B, well, part A is that find the top of the ladder sliding down the wall, the rate rather of the top of the ladder sliding down the wall. So we need to find dy dt. And B, we need to find the rate at which the angle between the top of the ladder and the wall is changing. So d theta dt. Okay, so now for our next step, step 2, we need to write an equation that relates all of these variables. So taking a look at the diagram, are there any equations that stand out that might be useful? Well, we're dealing with a right-angled triangle, so we can use the Pythagorean theorem. All right, so that theorem says y squared plus x squared equals 10 squared, which means y squared plus x squared equals 100. Now this, just recall, is just using those variables, x and y, not theta yet. So we're going to have to think about the next step. Or rather the next part after working out what we have here. Okay, so now we have step 2, which is step 2 completed, which is the relationship between two variables. One variable, we have information about its change, and the other variable, we need to compute some information. So then step 3 here, let's get it off of the shape for us. So step 3 is we need to take the derivative of both sides of that equation with respect to time. So on the right side, the 100, the length of the ladder never changes, so that's just 0. Then on the left side, we get 2y dy dt using the power rule, plus 2x dx dt. Both x and y are functions of time here. So that's why the derivatives come out for both. All right, so now we're on step 4. So we just need to plug in. We know dy dt. Actually, we don't know. That's what we want to try to find. But we do know dx dt. That is that 2 feet per second. So we can plug in that information. So now we know 2y times dy dt plus 2x times 2 equals 0. And now let's recall we know a little bit more information here. So we're also told, and maybe we can write that in the given, when the bottom of the ladder is 4 feet from the wall. So we know that x is equal to 4. And furthermore, we have the image then set up when x is equal to 4. So we have 10 feet here, 4 feet here, some y amount here. Now we can solve for y. So we know y squared plus 4 squared equals 100. So now solving for y, we get 100 minus 16 square root. So that is square root of 84. So we're only care about the situation when x is 4. So in this situation, the ladder falls. So the x value does change, but we want to know about the changes of the other quantities at a certain moment of time when that ladder is 4 feet from the wall. So then let's add to this given information. So x equals 4. We also know from the work we just did that y is equal to square root of 84. So let's also plug those values into our equation. And sometimes when we do problems like this, this is how it goes. We might need to go back and find out, oh, maybe there was more to what we were told than what we originally thought. Okay, so I can plug in a few more values here. Y is square root of 84. dy dt plus 2x is 4. And we already saw that dx dt was 2 equals 0. So now, super cool, look what we have is that we have an equation with just one unknown. And that one unknown is the change of y with respect to time, which is what we want to solve for. So now we can just solve for dy dt. So we subtract this 4 times 2 is 8, times 2 is 16. This is just 16. So we subtract 16 from both sides. And we get 2 root 84 dy dt equals minus 16. Now we divide both sides by that 2 root 84. And we see that dy dt is then equal to negative 16 over 2 root 84. We can plug this into our calculator and we get something like negative 0.87. And that's feet per second. It's really important to use your units. Let's add another page here just so we give ourselves more room. All right, so that would mean we can just summarize dy dt is about negative 0.87 feet per second when the x is equal to 4 feet. So if we look again at our picture, that means this y value is decreasing since the change is negative, which makes sense because our ladder is sliding farther and further down that wall. All right, so now let's take a look at how we'd solve for part B. So in part B, we're asked information about the angle between the top of the ladder and the wall. That's theta here. So for part B, we need to come up with an equation relating that x value, because we know information about dx dt, and theta. So we're on step 2 for part B. So we need to find equation between theta and x. Again, we need theta and x because we're given information about the change of x. Dx dt is 2. But we can use some trigonometry. So our image here is x and theta. How are x and theta related using trig? Well, x is the opposite side to theta. So we have that sine of theta is equal to x. And our hypotenuse here is 10. So it's equal to x over 10, opposite over hypotenuse. So here is our equation that relates theta and x. So now step 3 is we just need to take the derivative of both sides. So derivative of sine of theta dt equals derivative of x over 10 dt. The left-hand side, well, derivative of sine is cosine. So we get cosine theta d theta dt equals the 1 over 10 comes out and we're just left with dx dt. So now the only bit of info we need is to find out what the value of theta is when x is equal to 4. So we can just do that as a side. Theta equals what when x equals 4? Well, we can use this equation relating theta and x. So we have sine of theta equals 4 over 10. So this means we can use the arc sine to find that value of theta. We compute that arc sine. We get that theta is about, we're using radians here, we can just use radians throughout, is about 0.4115 radians. Okay, so we're almost there now. So now we just plug in, we're on the last step, we just plug in everything we know into the equation. So we know theta, we know x, but we don't even need to put an x there, and we have dx dt. So now we have cosine of 0.4115 d theta dt is equal to 1 over 10 times 2, because they're called dx dt is equal to 2. Giving ourselves more room here. So now we just need to solve for our unknown d theta dt. So to do that, we divide both sides by cosine of 0.4115. Now we get derivative of theta with respect to t, or how that angle changes with time, is 2 over 5 all over cosine 0.4115. We can consult our calculator and we get that our answer is about 0.22 radians per second. So this means that angle between the ladder and wall changes at 0.22 radians per second when the ladder is 4 feet from the wall. So this means that angle gets larger, our change is positive, which makes sense going back to our picture. As our ladder falls further and further, this angle gets larger and larger. Awesome. Great work going through problem 2, everyone. I know it seems like these problems are a lot of steps, but the more you do, the more comfortable you will feel. Keep up the hard work.